Well, good morning, all. Today we're going to start off our sixth chapter talking about current electricity. And uh, I'm not going to spend much time on the history of electricity. There's a video that I encourage you to check into. The only comment that I would make is that I just watched a video talking about the Baghdad battery, which is it was an interesting video in that there's now doubt whether it was actually used to produce electricity at all. So I'd be interested in anybody coming up with some more information on that. A lot of them claim that they did, and they used it for electroplating, and some now say that no, it's likely that the jar as it was actually used for what do they call it, storing scrolls, and the fact that the copper tube and the iron rod were found near each other in the excavations, jumping that to produce a battery is a bit of a leap of faith. So I'm not going to spend any more time on that. I'd like to just get into what's going on. Now I don't have my attendance in front of me, so I can't even recall how many of you have actually taken or are in the process, or no, I think you should be finished by now, taking chemistry 12 and talking about redox reactions. Well, if you haven't, here is the straight scoop. Those that have already seen this can turn your brain off for a little bit, but those who haven't, this is called a voltaic cell, and basically there are two containers containing ions of the metal electrode that is contained in there. Okay, so this could be, for example, copper sulfate or copper nitrate. Oh, I'm just going to be scooching a bit way out. Okay, there we go. And then this one here could be say zinc nitrate as well. We have a zinc electrode as well. So what happens here is that there is a difference between zinc and copper in that one of them has a greater tendency to lose electrons than the other, and that is capitalized on in galvanic cells. So if you were to take copper, I'm going to have to move it again. If you were to take the copper ions here and add 2 electrons to them, you would basically be taking the copper out of solution and plating it on here. And at this end, the zinc that is in the electrode has a greater tendency to lose electrons, and the ions would go into solution here. So basically what we would expect to see, based on reduction potentials, is that this has got a tendency to go there, and and to pick up the electrons that are produced and to form copper around here. Okay. At this end, the zinc has a greater tendency to give up its electrons, and then the zinc go into solution here. The salt bridge is just to complete the circuit, and our the way we can model, these are the voltages, the half cell voltages that are associated with both of those processes. Now this one here, you can see the copper ions gaining the electrons to form the copper metal is 0.15 electron volts. So I'm going to rewrite this just over here so you can see what's going on. Cu 2 plus 2 electrons goes to, and its half cell voltage is EO. Oops, can't see that. I should move it somewhere. EO is 0.15 volts. What's going to happen at this side, though, is that the zinc is going to split into zinc ion and electrons. So I have to take this existing standard reduction potential and change its direction. So basically what's happening here is the zinc metal is going to give up its 2 electrons and produce zinc ion. Okay? Now when I add these together, the 2 electrons that were produced here are used here, so the overall reaction eliminates those 2, so the net reaction is copper 2 plus ion plus zinc produces so really what we see here is just a transfer of 2 electrons from here to here. That's what we see. Now in this one here, the standard half cell potential is no longer negative 0.76. Because it's going in this direction, I change the sign, and this becomes 0.76 volts. So if I was to take a voltmeter and insert it here, my overall potential, so the potential of the cell, the entire cell, is equal to the sum of those, 0.91 volts. Okay? When we're talking, now most of you have got a sense of that. It's really, this is just maybe a bit of a commentary about the movement of electrons to begin with. That's fine. Let's move along. Electromotive force is, we use this symbol here, or it's measured, it is actually measured, electromotive force is the same thing as voltage, okay? So what electromotive force is the potential difference, so the potential difference which is the volts between terminals okay. So if we were I'll give you an example in a few minutes. The other way of thinking of this number of joules per coulomb of charge. So we can, so this statement tells us that 1 volt is equal to 1 joule per coulomb. Now when we talk about the difference between terminals, what we're saying is that what's the word? If you see something like this, this represents say a dry cell battery, where this is the negative end and this is the positive end. So we're talking about the potential difference. That is the number of volts between the positive and the negative. Now, if there is no conducting wire for the electrons to move in, there is no current, but the difference, the voltage difference, still exists. Okay. Now, once you complete it, the voltage difference goes to 0 because they're moving. Okay. Now, electric current is defined as the amount of electrical charge traveling by a point in 1 second. Okay, so the amount of electric charge that flows past a point in a circuit in 1.0 seconds. And we measure this in amps. I'm sure you've heard of amperes. That's the actual name, amperes, but we just shorten it to amps. And the symbol for it is just A. So 1 amp is equal to 6.2 times 10 to the 18 electrons per second. Okay? Conventional current and actual current are actually two different things. One of them is a crutch, the other one is reality. If I was to say set up a situation like this where I have, here is a circuit, and you'll learn the different symbols later, but this one, let's just put a light bulb here. Okay, I'm going to put a light bulb here. This is basically the 1-cell flashlight, and this, the smaller of these two, is the negative terminal, and the larger is the positive terminal. Now, the reality is that, okay, remember that an atom has all of its positive charge locked up in the nucleus, and its negative charges, the electrons, are sitting around it in a shell or a probability cloud on the outside of it. So the idea that positive charges can flow is actually absurd, because that would mean that the protons would have to leave the nuclei and flow. The only thing that actually can flow is the electrons. And so the actual current is the flow of electrons from the negative through the resistance, which in this case is a light, this way. So this is actual current. So I'm just going to continue with this red. This is actual current. Okay. Conventional current. Convention is a word that we use to say this is the norm, this is how we think of things. And so conventional current, it goes in the opposite direction. It doesn't really, but we think of it. There are some problems that are more easily understood if we can think of the conventional current going in that direction. So this would, you think of this as this is I, current going in this direction. So and then electrons going in the opposite direction. Okay? So this, I'm going to put this green. Still is green, right? Yeah. All right. Next thing up is this idea of drift velocity. And drift velocity is just how fast a free electrons move in a conducting wire. In chemistry, we don't talk about the electron clouds of metal so much, but it turns out that the electrons of metals, especially because they're some of the larger metals, larger atoms of metals, the electrons are farther and farther away from the nucleus, so they're more loosely held. And in fact, they actually kind of like form, I hesitate to characterize it as a soup, but it's sort of like that. They can be easily ripped off. Okay? So the drift velocity, I'll just continue this, is the movement of free electrons in a conducting wire. And often this will be measured in things like meters per second, or smaller, maybe centimeters per second. Okay, and we're going to do an example. All right. So the best way, we will use this strategy at the bottom. In order to do this, we have to make an assumption, though, and that's that every atom that is involved in this will allow the movement of one of its electrons. This is an average. It's an average, okay? So that's the first thing. The second thing is that we need to calculate the mass of metal needed to have 6.24 times 10 to the 18th free electrons. So we need to know the identity of the metal. Okay. Third thing is that we need to calculate the volume of the wire needed, and in order to do that, we have to know the density. So that's going to have to be a given. And the last thing is that we need to calculate the length of the wire to have the that number of electrons, so we need to know the radius. So that has to be given as well. So we need to know the identity, we need to know the density, and we need to know the radius of the wire. Okay? So let's do one on the next page. So this is just kind of like a visual. So here he is. Here's the problem. Calculate the average drift velocity of electrons through a silver wire. So that tells us what the identity is. So that's the first thing. Silver wire. And we need to know the length of the wire and we're given the diameter already. So here's the diameter here. So we only need to do length. So here we go. The mass of silver. So this is the first thing we have to calculate. Mass of silver. The mass of silver, oops, thank you, I heard Mr. Preeb yell at me. Mass is equal to the 6.24 times 10 to the 18 electrons divided by Avogadro's number per mole. 6.02 times 10 to the 23rd atoms per mole times the molecular weight, and we're going to use 108 grams per mole, just because yeah, I think it's 107.9, but it makes it easier. So 108 grams of silver per mole, and this is going to give us 1.12 times 10 to the negative 3 grams of silver. Okay? But does that make sense? Okay? The next thing, so what we've done here is we've calculated the mass of this silver here. We haven't figured out the length or anything yet, but we have calculated the mass. Okay? The volume of the silver wire. Oh, and here's the density. Let's underline the density. The volume is equal to the mass divided by the density, by definition. Remember our magic triangle. Density is mass divided by volume. Okay? The volume is equal to mass divided by density. We know the mass because we calculated it. 1.12 times 10 to the negative 3 grams of silver divided by the density, which is 10.5 grams per centimeter. And this comes out to, oh, I think it's 107. I'm reading off of something here. 1.07 rather, times 10 to the negative 4 cubic centimeters. Okay? So that's the volume. The radius, we have to invoke some of our, not geometry. Is it geometry? Yeah, I guess geometry that we've learned before. Is the radius of the silver wire is 1.0 millimeters, and so its cross-sectional area is pi r squared. So the length is going to be equal to the volume divided by the area. So length is equal to volume divided by the area. The volume we've already calculated. It's 1.07 times 10 to the negative 4 cubic centimeters. And the length, pi is constant, divided by the pi. R is 1.0 times 10 to the negative 1 centimeters squared. So the length is 3.4 times 10 to the negative 3 centimeters. Now the jump here is that it is this is how fast or how many centimeters an electron will go in 1 second, and that is the drift velocity. Okay, I'm going to stop there for now, and I will come back in the second video of this part, but I want you to spend a bit of time and rationalize yourself through this, and then we will continue on in the second video. Okay? Bless you. See you in a few.